Alright. Hello everyone. My name is Ahmed Kulinch. The main author of this paper was unable to make it to the conference, and so I'll be presenting in his place. I'm going to be talking about this case study on comparative analysis of 3D point clouds from UAV-mounted and terrestrial scanners for bridge condition assessment. Alright, let's get into this. So, first let me talk about the 3D spatial technologies that exist in present time. Recent improvements in 3D laser scanning technology have enabled accurate capturing of existing spatial conditions using point clouds. And a few of these alternatives, and each alternative has its own unique set of specifications that it is optimally oriented for. For example, the first one are are handheld laser scanners. Then we see options including terrestrial scanning, then mobile ground scanning units, and then scanning units attached to micro UAVs, and then airborne LiDAR capturing units. Now, each of these units have, as I mentioned, are uniquely created to fit a different scenario, a different scene size, and a different scene complexity. Handheld scanners are incredibly versatile in capturing scenes of different complexities, however, are severely limited to smaller scene sizes. On the other end of the extreme, we can see airborne mobile LiDAR scanners, which can capture very extensive scene sizes, but are limited to very small scene complexities. For the structure of focus of this research project, bridges, the medium scene size scanning alternatives are very, very optimal. These alternatives include terrestrial scanners and include micro UAV mounted scanners. Terrestrial scanning, compared to the micro UAVs, are limited to a smaller scene complexity due to the number of points at which they have to be installed and at which they must take 3D scans, while meanwhile micro UAVs can be applied to scenes of higher complexities. Now, once we collect this data, we're trying to understand if the main focus of this paper really is to understand if when we have this data, if the data is suitable for not only for the data collection, but also for the for use of the data for condition assessment purposes. And this becomes even more important when we consider the different types of common errors that can occur when considering point cloud data and the collection of point cloud data. There can be issues with the coverage, including clutter and occlusions, issues with the resolution, including varying point density, and issues with quality, including having very highly noisy data. And so this raises the very critical question, is the data collected suitable for condition assessment as per federal guidelines? And that is the primary focus of this paper, and we're going to be going into that in just a second. Okay. Now, before I go into the rapid preliminary assessment methodology, let me give you some background on the condition assessment process and what we do with the data once it is collected and how we analyze that. So we have a bridge to start with, and currently there are two common methods for collecting this data, and right now visual inspection is much more prevalent, which includes engineers or maintenance workers getting on top of a crane and going to the various points of the bridge to check all of the different structural deformities that might be occurring at those points, and then create a very long, complicated inspection report from this analysis. The method we're going to be focusing more specifically on is the laser scanning method, from which we can install terrestrial land scanners at several different points, critically selected points around the bridge, or we can get a UAV and attach a LiDAR scanner to this UAV to eventually create a 3D point cloud, which contains X, Y, and Z coordinates and RGB information for each of these points. Now, from the data collected we analyze this data in terms of the defects that the bridge structure may contain. And we have several criteria for doing so. This criteria includes the extent of the defect, the color of the defect, the location, and its overall context. Now, an example of it is up here as a defect commentary. And then eventually this data, the extent data, can be used for separating each of the defects into several condition states based on the severity of the defect and its urgency for being addressed by engineers and structural maintainers. Now let's talk more about the case study that was done for this project. The case study was conducted on a bridge in the Pennsylvania area, thanks to the Pennsylvania Department of Transportation. And we conducted two main scans for the area. One with a terrestrial scanner, the Faro-focused 130, which has a range error at 10 meters of 2 millimeters and a range noise of 0.3 millimeters. And then we equipped a UAV drone with a state-of-the-art Velodyne VLP-16 scanner, which has a range error of 30 millimeters at 10 meters and 5 millimeters, or a range noise of 5 millimeters at 10 meters. If you look at the upper side, you can see that you compare the UAV scan on the upper left to the terrestrial land scan on the upper right. The primary difference between the two is that the terrestrial scan, as you can see, has a higher point density in most areas, but the UAV scan has more uniform data. Since the UAV is able to reach points the terrestrial scanner possibly could not have, due to the terrestrial scanner's limitations of having to be placed at several different critical points. And here's the drone that we specifically used. It was installed with several other sensors, including a GPS, an inertial motion unit, the 3D LiDAR I was just talking about, a spherical camera to capture RGB information, and then an Intel i7 computer to turn all of this point cloud data into an actual point cloud. While it is in the process of flying, before it lands, it actually gives us the model. More specific about the case study, you can see on the diagram up here the several different points that the terrestrial scanner was placed at to contain these scans, and the path that the UAV flew through to conduct the scans of its own. And I mean, you can see that the point cloud from the terrestrial scanner has roughly 12 million points, while the one from the UAV scan has 4.8 million. So there is a distinct difference in the total number of scanned points from the two scanning alternatives. Now I'm going to go more in depth on the specific metrics that were determined from this research process. Now, I'll be talking about two primary ones, the PPD metric and the GND metric. The PPD metric, also known as the point plane distance metric or the distance metric, is more relevant for out-of-plane defects such as spalling, primarily. And then the GND metric is more relevant for in-plane defects such as cracks and section loss. The GND, by the way, refers to grid neighbor distance. Now both of these metrics have their own very unique set of methodologies, but they both contain several common steps such as defect scale extraction, point cloud segmentation, and plane extraction. That has to be done before any of the other processes. And I'm going to go more into these common steps right now. So defect scale extraction refers to our taking of the extent of several defects and putting it under certain scale thresholds set by federal guidelines. For example, I'll walk you through the crack guidelines right here. If a crack is of width less than 0.012 inches, or has spacing greater than 3 feet, then it's considered to be put under condition state 1. And if the width exceeds this and exceeds the 0.012 inches and goes up to 0.05 inches, or the spacing varies as well, it's a CS2 and so forth. And these scales are incredibly important because they'll be used as primary scale metrics for the two data assessment metrics that we've developed here. And I'll go more into that in just a second. Let me talk more about the plane extraction process here. So for example, we have the entire 3D point cloud of the bridge. Then the bridge, you can see, is separated into several segments. And if we focus on the abutment over here, we can see that it is extracted and then further separated into several planes that can be individually analyzed for more accurate and uniform data. And each of these planes is put through the metrics that we've developed, the PPD metric and the GND metric, under these scale values that I just mentioned in the previous slide. Now let me talk very specifically about the metrics themselves. So the distance, the PPD score metric, as I mentioned, is incredibly useful for understanding out-of-plane defects, and this primarily includes spalling. And so first what we do is we, after extracting the planes, After extracting the planes, and once we have the 3D point clouds, we try to fit a computational plane to these 3D point planes. For this, we use the MLE-SAC algorithm, which is a variant of RANSAC. And this algorithm requires a distance threshold, which is used to pick points that will ultimately be used to generate a computational plane. And these distance thresholds, in this work, we're going to be using the defect scales that I was talking about several slides ago as these distance threshold values. And at each threshold value, we count the total number of points that contribute to the computational plane, and the proportion of these points to the total number of points in the 3D point plane. And this overall value is the PPD score for the plane. Now, because of this method, the higher the PPD score, the higher the chance for us to use that data for condition assessment in terms of these defect scales. For example, if the PPD score is high at a CS3, a more severe condition state, then the data could be used to detect a CS3 scale defect. But if the defect becomes much smaller, say falls under the CS1 category, then we can expect the PPD score of it to drastically decrease. And this large decrease corresponds to a decreased chance for us to actually detect the defect and suitably use it for condition assessment. And you can see a similar state here that I was just talking about with the UAV scan that had a PPD score of 78.98%. We can reasonably use it to detect CS3 and CS4 level defect conditions. Meanwhile, for the terrestrial land scan, which has a significantly higher PPD score, we can use it to even detect CS2 level defects. All right. Now let's talk about the grid neighbor distance metric. As I mentioned, this is very useful for in-plane defects such as cracks and section loss. In this method, we create grids with spacings based on the different metric sizes. And then onto these grids, we superimpose the 3D point planes that we extracted in an earlier step. And we go through each grid intersection point. You can see that happens at the corner, at the intersections of each of these lines here. And we find the shortest distance from that point to the nearest true 3D point that we took from the overall scans themselves. And from these, and once we get all of these cumulative distances, we find a cumulative sum. But the thing is, not every scan has the same number of points. As I mentioned with terrestrial scans, they have roughly 12 million points, and then UAV scans have roughly 4.8 million. And so what we do is to normalize all of this data, we divide it by the total number of true points in the 3D point plane and create what we call the GND score. And the smaller the GND score, the better it is, and the better the data is the more suitable it is for condition assessment. And the premise for this methodology is that the 3D points are dense and uniformly spaced. The cumulative distance, if that's the case, the cumulative distance between the grid intersection points will stay low, as opposed to if they are not dense or if they are not uniformly spaced. And you can see an example of these results right here with when we have a 0.0 1/8 inch grid size, then we have higher GND scores, and as opposed to different sizes, and we can see this comparison go on as we get new types of data. And let me go into some conclusions. We can see that if we look at the two metrics that we found, the PPD score metric that we developed is extremely useful for out-of-plane defects. Meanwhile, the GND score metric is very useful for in-plane defects, and this could be used in sets of future research by or even by individuals in industry. We can also see that our results suggest that scans from UAV scanners are currently, at their current stages, capable of supporting only CS3 and CS4 level defects. And meanwhile, scans from terrestrial land scanners can additionally help to distinguish between CS2 and CS3 level defects. And our current work only utilizes 3D spatial data, and efforts are on to utilize other information such as color density and color and intensity to achieve a more complete evaluation of these 3D point clouds. And we can see the future work comprises process analyses of using these two nodes of scanning to better quantify the benefits and their impact on the condition assessment of bridges. The authors would also like to acknowledge the NSF for providing us grants, Pennsylvania Department of Transportation, Carnegie Mellon Robotics Institute, and Michael Baker International. Thank you.